Good morning.
Good morning, sir.
Good morning, sir.
Okay. Yeah. So uh, we are 21 now. Anyway, let's start. So sometime next week, maybe, because I think next week will be the last week before the puja vacation. So I think we can have a class on the doubt clearing, whatever doubts you have from what we have learned so far. So that class we can discuss. Okay. So I think these things we have all covered in the last class. Command, power systems. So we were talking about uh, the initial part of communication subsystem. So one of the things to understand is that the uplink signal from the Earth station to the satellite, that also is a weak signal. Okay. But then the question arises that is it possible? Can you hear me, everybody?
Yes,
Yes,
sir.
sir.
Okay, so the question arises that then does it mean that we also have to put, very large aperture antennas on the satellite itself because the uplinking signal is weak. So now that is not a possible option in case of onboard satellite antennas. You cannot put large structures. I was mentioning that at the Earth station you can build larger and larger antennas. Like in the early 60s and 70s, the trend was that to go for even 100-meter diameter aperture antennas. But that was on the surface of the Earth. We cannot think of having, kind of a 100-meter diameter antenna or even 50-meter diameter antenna on board a satellite. So the power that is received from the uplink on the satellite, that will also have a low signal to noise ratio. By now I think you are familiar with the fact that in order to quantify the quality of a communication link, whatever kind of communication it may be, the parameter which is used is known as the signal to noise ratio. Okay. And uh, the frequency bands which are mostly used for satellite communication, they are like the 6-4 gigahertz, 14-11 gigahertz, a pair at a time, and 30-20 gigahertz. Now the first question that comes to the mind is that why are these frequencies in pairs? When they are in pair, it means that essentially we are having two different frequencies, one for the uplink and the other for the downlink. Okay. Now the first point to consider is that uh, these frequencies need to be different for the transmission path to the satellite as well as the downward, receiving link at the earth station, at the receiver earth station, because one of the reasons is that there may be, interference from one frequency onto the other, because if they were at the same frequency, then the receiver on board the satellite will find it difficult, will not be able to, discriminate or differentiate between the uplink and the downlink frequencies until and unless some kind of a discriminating factor is introduced in the signal itself. That discriminating factor may be some code, but then without going into that kind of a complexity, what is usually done is that the two frequencies are kept different. And also, if the different frequencies are not used, then the high power these signals, they may overload the receiver if both of them are operated at the same frequency. Now, among the two frequencies, once again, the question comes that which one to use for the uplink and which one for the downlink. Now, when we try to answer that question, we should keep it in mind that uh, for the uplinking signal, that is from the Earth station, transmitted at the Earth station to the satellite, the directivity of the transmitting antenna has to be very high. Okay, because from the Earth station transmitter to the satellite, it is almost like you are pointing towards a small speck in the sky. I mean, speck not in terms of that you can actually visualize it, but in terms of that satellite and the adjacent satellite being very close to each other, as we know nowadays. So, for that reason, higher directivity is required. And in case of antennas, you know that the directivity and the gain, they have the same expression numerically, but their units and interpretations are different. So directivity is also inversely proportional to the square of the wavelength, right? 4 pi effective aperture by lambda square. I think you know these relations, right?
Yes, sir.
Yes.
Yes, sir.
So the directivity is also inversely proportional to the square of the wavelength. That means directly proportional to the square of the wavelength. So higher is the directivity, higher is the frequency of the signal, greater will be the directivity. So for that reason, the uplinking signal is usually having a higher frequency, like say 6 gigahertz or 8 gigahertz, while the downlinking frequency, that is one which is being transmitted from the satellite over a geographically distributed user base. I mean, suppose for the entire Indian subcontinent, including some portions of Pakistan, Bangladesh, Burma, and so on, Myanmar, and so on. So, uh, that means there, because it is some kind of a broadcast signal, it is not intended for a particular desired user only. So, the directivity requirement is less for the downlinking signal because it is a broadcast signal. It is meant for everybody. It is not something classified or meant only for a select user. So that is why the lower frequencies are used in case of the downlinking signal. Now, among these range of frequencies like 6.4, 14.11, or 30.20, okay, the 6.4 is the most commonly used pair of frequency even today for satellite communication. The 1411 gigahertz is used, but it suffers from some problems because one of the absorption bands of water vapor, they lie around that 11 gigahertz range. So that causes a lot of attenuation. Water vapor causes a lot of attenuation of the of radio signals, particularly microwave signals. And so that band has certain problems, but it also has certain advantages. Okay. And the problems that they face, we can also understand that, in case of railway reservations, sometimes we have this experience that if there is a very heavy rainfall, then sometimes that microwave railway reservation link that gets a failure, that develops a failure. And the 30-20 gigahertz frequency band, that is very rarely used because first of all, we should keep this in mind that for any kind of communication system, the cost of the equipment increases as we go to higher and higher frequencies. And that increase is not linear also. Like from 6 to 14, it is not like the price will double. The price is likely to go up by, say, 2 to the power n times. Okay, that means 2 to the power 2 times in this case, say. So almost 4 times there will be increase. So the 30-20 gigahertz band, it does not suffer too much, although there is another water vapor absorption line around 22 gigahertz, but it does not suffer too much from these effects. Uh, but then, because of the very high cost of equipment, it is almost never used for commercial applications, for civilian applications. The military uses this band because they have, certain restricted operation, and it is not like public domain. It is not like in the public domain. So the military does use this 30-20 gigahertz band, but it is almost never used for any kind of civilian applications. Now, the next thing that we should learn is that uh, on board a satellite, let me see if I have the picture. Yes. Yes. Now, one of the important things to consider is that on board a satellite, we have a device which is known as a transponder. Okay, just like when you visit your nearest cable operator office, you will also find that they are sometimes referring to transponders for a particular service, and that transponder is actually on board a satellite. It is a kind of a combined device which has the capability of both receiving the uplinking signal, doing some processing on the signal. I will come to the details of that processing a little bit later on, and retransmitting that signal. Okay, so all these three stages, first reception, then some kind of processing of the signal because the received signal is extremely weak, so it has to be amplified before you can perform any kind of operation on that, and then retransmission of the signal for the desired user. That device is known as transponder. So the first generation or early communication satellite transponders, they had bandwidths of about 250 to about 500 megahertz. Okay. Now these transponders on board a communication satellite, uh, they are their use is more efficient if their resources, if these resources are shared among a number of users. Okay, I mean, it should not be that a particular country has launched this satellite and uh, only a single user can access this satellite transponder at a particular time, because that is a very poor utilization of this very expensive device. Designing a satellite and launching it in geostationary orbit is very expensive. I had mentioned about it's more than $1 million for 1 kg of object. So that is why this 250 to 500 megahertz bandwidth, that should be distributed among among as many users as possible. Now, these early generation communication satellites, they had, of course, the antenna technology in the 1960s and 70s, and also in the early 80s was not so much developed. Okay, and the transmitters, they were outputting powers which were like only about 1 to 2 watt. So that's why you can understand that the received signal uh, at an earth station, that is only of the order of like, the power associated is only of the order of 10 to the power minus 10 watts or so, after traversing a distance of nearly 40,000 kilometers. And when I say this 40,000 kilometer, don't think I am doing this distance calculation from the center of the earth. No, because you might say that, sir, the orbital altitude of a geostationary satellite is only 36,000. But that 36,000 kilometer is the nominal orbital altitude. That means when it is vertically overhead a particular location. But geostationary satellites over the service area. But geostationary satellites are always located, you know, some degree either east or west of the longitude or the user base which it has to serve. So that's why the distance of the satellite from the Earth station, that increases above 36,000 kilometers. Typically, it's like 39 to 40,000 kilometers from a particular Earth station. Now, hello,
Yes, sir.
Yes,
yeah,
sir.
did anybody ask a question now? Just now.
No, sir. No, sir.
Okay. So, what happened was that this total channel capacity, say for example, this 250 megahertz, that could, that could accommodate, if we can do some calculation, we will see that that could accommodate something like about 10 to 12 users at a particular time. So, what we can see over here is that these early transponders, they were having bandwidths of only about 250 to 500 megahertz, but we can, through some technique, increase the effective bandwidth to be about almost like 2500 megahertz or 2.5 gigahertz. Those techniques are known as, frequency reuse techniques. We will discuss them. But before that, I'm just trying to look at, yes. So as you can see, that suppose, okay, before coming to this, now these different frequency allocations for the different regions of the earth, they are done by the International Telecommunication Union. So when we say that we are using, suppose, the 6 4 gigahertz, 6 gigahertz for the uplink and say 4 gigahertz for the downlink, what we mean is that every country or every region is allotted a center frequency about which a certain bandwidth is allotted. Okay, it is not a single spot frequency which is allotted. The carrier frequency at the center with a certain amount of bandwidth. So, like for example, for India, the downlinking frequency may be varying from about 3750 to 4250. Suppose it's a 500 megahertz bandwidth. Okay, 3750 megahertz to 4250 megahertz. So this is like 500 megahertz bandwidth is allocated now for the entire country. So out of those, once again, one has to, kind of do some kind of a efficient allocation or division so that many users from India could actually use that frequency. Otherwise, it is a kind of a wastage if only one user uses that at a particular time. So that 4 gigahertz downlink does not mean that it is only at 4 gigahertz. There is a band of frequency around that across which the particular user can transmit and can receive signals. So uh, there are different regions of the earth classified by the International Telecommunication Union, like the region 1 is Europe, Africa, sorry, and the northern part of Asia, and region 2 is North and South America, and region 3 is the remainder of Asia. Okay, and we can understand that perhaps the largest chunk of frequency is allocated to region 2, where at least traditionally the use of satellite communication users was much more. The number of satellite communication users was much more. Now, when we talk about, this transponder, so suppose we are having this particular, schematic. This is an example where you can see we are having a particular band extending from about 3700 to 4200 megahertz. And within that, there are like different carrier frequencies allocated, so 3720, 3740, 3760. That means each is separated from the other by about 20 megahertz, and uh, the carrier frequencies. And around that carrier frequency, there is a bandwidth of total 36 to 40 megahertz. That means, as you can see, this 500 megahertz channel, the 500 megahertz bandwidth from 3700 to 4200 megahertz is divided into a number of channels which are like 36 to 40 megahertz wide, and each of them is handled by a separate transponder. Okay, now over the years, experience of satellite communication has taught us, the system designers, they now know better that instead of having one large bandwidth transponder, it is always better to have more number of narrower bandwidth transponders. Okay, because that will avoid this problem of intermodulation, wherein some kind of spurious frequencies may be generated by the beating of two frequencies which are simultaneously present in the system. So, one of the things that we should try to understand, and similarly, this is for the transmit, that means from the ground based earth station to the satellite, these frequency allocations or these frequency divisions are used. And for the downlinking also, suppose from 5900 to maybe 6400 something megahertz, this range is used because, as I was telling you, that 6 gigahertz does not mean that the uplinking frequency is only at 6 gigahertz. So this is for the earth station to the satellite, and this is from the satellite to the ground station, the ground receiving station. Now, as we can see that when this 500 megahertz is divided into 40 megahertz channels, okay, as we can see over here, 40 megahertz, 20 megahertz on either side. So if it's 40 megahertz and the total is 500, then we can at best accommodate 500 by 40 is something like 12 point something. That means we can accommodate about 12 users at a particular time. Okay. Now, Having a transponder in a communication satellite and you know that being used by only 12 users at a time is not a very efficient use of the system resources. So that is why what is needed is that we need to have some technique, like for example frequency reuse, to increase the total channel capacity of the satellite. Like one of the techniques which is used is spatial frequency reuse. Okay, so it essentially means that from the satellite, instead of having a single downlinking beam, if we can use several directional beams at the same frequency, maybe one of the downlinking beams is pointed towards the Indian subcontinent, the other towards the Southeast Asia, and the third maybe towards some portions of Central Asia or Middle East. Okay, it may not cover the entire region. So that way you can see that as the number of users increases, so that results in increased amount of revenue for the system, because eventually you see the designers or the company which has launched that communication satellite, they would like to get their entire cost back within say 5 to 6 years of operation, because the active lifetime of a geostationary satellite is something like 8 to 10 years. So they would like to break even maybe after 5 to 6 years. And with that objective, they also have a motivation that if they can increase the number of users to some, technological innovation like this frequency reuse techniques, then they can, of course, have a much better utilization of the resources on board the satellite. So, having different directional beams at the same frequency, okay, because that downlinking frequency, it will become difficult or more complicated if we are using, different frequency beams for in different directions at the same time. So, without complicating the things any further, one can achieve uh, having one can achieve this objective by using several directional beams at the same frequency. And then comes the technique of polarization frequency reuse. Okay, that means one of the characteristics of electromagnetic signal or a radio signal, which is very often neglected, is the polarization. We are mostly concerned with the amplitude, frequency, and phase of the signal. But the fourth important parameter or characteristic of a radio signal, which is the polarization, that is mostly forgotten by us or overlooked by us. So, if we can use, some kind of orthogonal polarization at the same frequency and generate multiple number of users, that means instead of, having a fixed set of users using or tracking a signal at a single polarization, if we can generate two orthogonal polarizations at the same frequency in the downlinking beam, then we can, of course, double, at least double the number of users accessing the satellite based transponder at a particular time. Now, we should remember that uh, all these techniques are used only for the downlink, okay, not in the uplink. In the uplink, it's a straightforward transmission from the ground-based earth station to the satellite. Only when it comes to downlinking beam, that means that is where actually, the revenue stream is generated. That is where the more is the number of users, more the number of users who are accessing the satellite at a particular time, greater will be the revenue generated, and also greater will be the utilization of the resources, because that is also an important thing. Like in the case of INSAT, say it's a government of India, ISRO, Department of Space, their satellite. Okay, so they are not into kind of in a revenue generating mode. They do not operate that way. But for them also, having launched a very sophisticated, expensive, and very big communication satellite, if the users are limited, then that is a very poor utilization. It does not justify the huge cost which is involved. So that's why, from that perspective also, not only the revenue part, but from that perspective also, it is important that you need to have larger number of users accessing the transponder on board a satellite. And through this technique of either polarization frequency reuse or spatial frequency reuse, that means spatial frequency reuse, you should try to understand that we are using spatial as well as frequency in the same term. Yes, because the general name is frequency reuse, and what we are doing is that we are generating a number of spatially separated downlinking beams. Okay, their information content may or may not be different. Okay, like for example, sometimes the very modern generation of communication satellites, they do have that technique, that suppose a particular satellite is transmitting for the Indian subcontinent as well as for Southeast Asia. Okay, where there are Indian settlements also, like in Singapore or some other place like that. So when the morning news is transmitted, then in the Singapore time, early morning time, so that may be just after midnight in India. So it makes no sense to transmit the same information content for India and for Singapore at the same time. There may be some kind of a time lag, and within that time lag, the news may also evolve. So that's why the information content of these spatially separated beams may or may not be different. Okay, like for example, when a live football match, say for example, is being telecast, so then of course you whatever is there, you transmit it, and the information content will be the same. So through the effective use of these frequency reuse techniques, sometimes a simple 500 megahertz band transponder at 64 gigahertz can have number of users which is equivalent to having an effective bandwidth of 2250 megahertz. So like 4 times you can multiply the number of users. Be careful. This does not mean that the hardware itself it changes from 500 megahertz bandwidth to 2250 megahertz. It's not that. What we are trying to say is that the number of users that is increased through the use of these frequency reuse techniques, so that the number of users becomes equivalent to an effective bandwidth of 2250 megahertz. That means if you had a bandwidth of 2250 megahertz, then the number of users which you can accommodate over that large bandwidth, you are achieving that number of users with a 500 megahertz band at 64 gigahertz. So, uh, the next thing to consider, so you see this communication subsystem, there are several intricacies involved. First of all, we have to understand that the uplink and downlink frequencies are not one and the same. They are different, and there is a definite reason why they are different. Secondly, which one of the two frequencies to use for uplink and which one to use for downlink. Then thirdly, the frequency which I am uplinking, that is say around 6 gigahertz uplink, and the downlink is say around 4 gigahertz. I am just taking that example because the 6 4 gigahertz band is the most commonly used band. Okay, we have other frequency bands at 1411 and also 3020, but this 6 4 gigahertz is the most commonly used. So I'm taking that example. So that means I'm transmitting an uplink signal at 6 gigahertz and receiving a downlink signal at 4 gigahertz. So that means somewhere within the transponder there should be a mechanism to down convert the frequency from 6 gigahertz to 4 gigahertz. That means at the input of this transponder, the frequency which is received is like 6 gigahertz, but the frequency which is transmitted at the output of the system is at 4 gigahertz. So there has to be some kind of, uh, down conversion of frequency within this particular system. And because the transponders, now we realize that the transponders, they are the heart and the soul of the communication subsystem. So there should be multiple number of transponders in order to increase the number of users, and also there should be some spares, some spare transponders also on board the satellite, so that we are in a position that if some of the transponders they suffer a failure, then we still have sufficient number of other transponders to execute the work. Now, when we talk about this frequency, down conversion of frequency within a transponder, then basically we can understand that whether we are talking about the 6 4 gigahertz or the 1411 or the 3020, there may be different down conversion strategies or different down conversion principles which are used. Okay, like for example, this picture shows that for the 6 4 gigahertz on board the satellite, you have a 6 gigahertz receiving antenna. Then that is followed by a low noise amplifier, okay, which may be a gas FET amplifier. Then the down conversion happens here where you have a local oscillator around 2225 megahertz. So this is like 2.225 gigahertz. So when you beat the 6 gigahertz with the 2225 uh, megahertz local oscillator signal, you get at the output some frequencies which are close to 4 gigahertz, and then you have an RF band pass filter around 4 gigahertz. So the output of that you put into a preamplifier, RF preamplifier, of course. And finally, before transmission, because the signal once again has to traverse nearly 40,000 kilometers before it is received by Earth station, there are some high power amplifiers. Okay, and finally we have a 4 gigahertz transmitting antenna on board the satellite. Now, this is what is known as a single stage conversion or down conversion of frequency for the 6.4 gigahertz. And there are very strict requirements on the filters used in transponders, since these filters, they actually should provide very good rejection of the intermodulation products. Okay, so that otherwise, what will happen is that the frequencies which are out of band, they may also get coupled onto the RF amplifier, the high power amplifier, and effectively that will result, in a poor utilize in the once it is transmitted, the receiver at the ground will not be able to uh, receive those signals because they are out of band. Then, for the double stage frequency conversion, which is usually employed for the 1411 gigahertz, we have 14 gigahertz receiving antenna, and that is followed by a low noise amplifier once again. So the uplinking frequency in this case is at 14 gigahertz. Then the down conversion, a down conversion in frequency happens first of all because you have a local oscillator which is around 13 gigahertz, and that results in an IF around 1 gigahertz. So that IF around 1 gigahertz, that is then passed through an amplifier. Now around 1 gigahertz, because the devices and components are easier to design around 1 gigahertz than at higher frequencies. So this is the 1 gigahertz IF amplifier. Then that signal now has to be up converted to 11 gigahertz. So we use a second local oscillator around 10 gigahertz in order to and beat it with this 1 gigahertz signal, and we get at the output 11 gigahertz signal, but we still use some kind of a RF band pass filter in order to remove the out of band noise or signal, and finally pass it through a high power amplifier in order to provide it with the necessary amplification. And then finally we have this 11 gigahertz transmitting antenna. So this is a two-stage conversion. Okay. Now, there are some critical issues to consider when we talk about either the single stage or the double stage system, the double stage conversion in a transponder. So, you have to understand that all these two techniques, whether it's a single conversion or a double conversion, this is happening on board the satellite. Okay. Now, one of the things to consider is that there may be, different kinds of multiple accesses used. Now, I'm just, debating whether to go into this right now or not. Uh, have you read anywhere about the multiple access techniques in any of your communication classes, digital communication?
No, sir.
Okay. Um, okay, then let us, without going into this multiple access right at this point of time, let us just try to understand that, suppose we can understand that whether you are that means from the satellite, when you are transmitting the signal down towards the receiving earth station, once again you need to ensure that the signal has sufficient amount of power. That means you want to have very good amplification of the signal, like we were seeing over here, this high power amplifier, this one or that one. So you would like to ensure that the amplification of the signal is very high before it is transmitted. So that means that for that purpose, the output power amplifier, this has to be uh, driven into the nonlinear region of its characteristic. When we typically discuss about, the output characteristics, we know that there is a linear portion of the output characteristic of an amplifier and a nonlinear portion. So when we drive the amplifier in the nonlinear portion of its output characteristic, we can understand that there will be some spurious frequencies which will also be generated. You will be achieving a higher value of amplification, no doubt about it, but at the same time there will be some additional spurious frequency components generated. Okay, so in order to avoid that, what is being done is that the operating point or the Q point of your amplifier or device, that is actually moved back to the linear region of operation of the output characteristic. Okay, so that means that once you operate in the linear region, the maximum output power that you get is less than what you were getting when you were operating it in the nonlinear region. But at the same time, what has happened is that you now have almost no intermodulation product or no spurious frequencies to deal with, no additional frequencies to deal with. Now, this amount by which the operating point is shifted back from the nonlinear to the linear region of the characteristic, or the degree by which the transmitter output power, that high power amplifier output, is reduced below its peak value, that is known as the output back off or OBO. So you are deliberately reducing the output power of the transmitter on board the satellite so that you do not have to face the problem of, you know, uh, intermodulation products or spurious frequencies being generated. I think I will stop here today, and we will continue with this in the next class, because this communication system and subsystem and the link uh, equations are most important over here. Now let us have the attendance. 301,
Present, sir.
302,
Present, sir.
303,
Present, sir.
305,
Present, sir.
306,
Present, sir.
308,
Prancer,
309,
Present, sir.
311,
Present, sir.
313,
Present, sir.
314,
Present, sir.
315,
Present, sir.
316,
Present, sir.
317, 318, 319,
Present, sir.
320,
Present, sir.
321,
Present, sir.
322, 323, 401,
Present, sir.
402, 403, 405, sorry,
Yes, sir. 405.
407,
Present, sir.
408, 411,
Present, sir.
414,
Present, sir.
420,
Present, sir.
421,
Present, sir.
422,
Present, sir.
423, 424,
Present.
430, 431,
Yes, sir.
432,
Yes, sir.
433,
Yes, sir.
435, 436,
Present, sir.
437,
Present,
438, 439, 440, 441, 442, Chayan Datta,
Present, sir.
Ravi Kumar Thakur. Thank you.
Thank you, sir.
Sir, 423 present. My mic was not working.
423.
Yes, sir.
Okay.